All right. Okay, so let's go back to our notes. All right. You see, we call this uh, A, like this one. Oh, just write this down. Convergence set here. The convergence set always somehow symmetric. This is symmetric to 0. Here. Okay. This one, the other one. This is symmetric to 2 because this is the center is 2. Symmetric. So distance 1 to the left, distance 1 to the right. So centered at 2. All right. So this is the idea of what we call a here rho. Rho is the radius of convergence. Okay. So this is radius convergence 1. Okay. So here we have convergent radius, or rho is 1. Same thing here. Here's also convergence radius. Okay. So let's see the convergence radius. There are 3 types of convergence radius. For example, this one here. And just this one. Centered at 0, that's easy. Or in, I get something more extreme. Say this one. Okay. So let's check here. So let's do the absolute ratio test. So an plus 1 over an, absolute value. Okay. So this gives you n plus 1 factorial times x to the n plus 1 n factorial x to the n. Absolute value. And factorial over n factorial. So there's n plus 1. And next is just x, absolute value of x. Okay. And so the limit is just limit of n plus 1. So then what's going to happen here? Well, this is goes to infinity, of course. Right? So the limit here is going to be let's see. Yeah. Okay, this is going to be 0 if x is 0. Okay, and it's going to be okay. If x is something non-zero, then absolute value is positive. Then this goes to infinity, and this is divergent. Okay, so you see that the one that gives you less than one is bigger than one. So we only have convergence at one point. Okay, convergence only at x equals 0. Okay, so what we have here is that radius convergence is, so say convergence set is there. Radius of convergence zero. Okay, so only that point. Another example. All right, so let's put the factorial as a denominator. So by absolute ratio test, here is, and we have what n plus 1 over n plus 1 x to n. Okay. So this n, so yeah, then you have just it. Okay. So then this gives you 1 over n plus 1. So the limit is just x limit. But this goes to 0. Okay? So this is always 0. All right. So this is always the case for any x. So this doesn't depend on x. So the conclusion is that now this is convergent for every real number. Okay, so that means the convergence set is this. Okay, and the radius of convergence is all right. So this is the two extreme cases. You have radius 0, meaning convergent only at the center. Here you have radius convergence infinity, means that you have everything converges, right? And a lot of in the middle. Okay. All right. So in fact, you get this formula. If you want to say the radius of convergence, you see that this is, in the end, when you compute this one, let's check. The end, take the end. So this is our an. Okay. This is just limit uh, cn. Sorry, one n plus one. Hopefully, you take always take the absolute value of x out, and you have this limit cn plus one over c. Yeah? Assuming this is positive, or you can take this one. Doesn't matter. Okay, so you want to make this convergent less than one. To make convergent. Well, that means x is, if you solve this, you get x should be less than 1 over limit. Okay, so this is the radius of convergence. This row. So this is an explicit formula to find radius of convergence. Coefficient. C is coefficient. A is the term. So that's the difference between term and coefficient. So that's row. Okay. All right. Of course, sometimes you write this down as, if you don't like this 1 over, you can take this out. So then there. Okay. So that's the formula for explicit formula for radius of convergence. Okay. Questions? Okay. If not, then let's go. Uh, okay. So problem 8. Okay. So this is the case. Um, this is what we call operations. Absolutely convergent power series. Okay. So if you have power series, okay, absolutely convergent power series, there's a lot of things you can do. Say, radius can be applied to convergent, to absolutely convergent. Okay. What kind of operations? Well, you can do arithmetics. So that means you can do summations, subtractions, You can do multiplication, you can do divisions. Of course, if you have divisions, then you must avoid zero. Okay? And you can do calculus operations. That means limit, uh, differentiations, and integrations. Okay, so what does it mean here? Um, okay, let's do this one. Um, Start with I would like to show you this going to this type of problem here. Problem 7. Okay. All right. So let's see. For example, this is the base. The basic thing. The basic thing that you always start with this one. If you think about this one, x to the n. Okay. So this is just 1 plus x squared. Okay, what kind of series is this one? You recognize this series. Of course, this power series, but what else can you say about this series? What kind of series is this one? Hello, is anyone there?
Is it geometric series, sir?
Geometric. Uh, Now this is geometric series. With what we call this the ratio, right? Uh, Ratio x. Okay. So what should be the limit? What's the limit? Because the ratio is just x. So what's the limit? Limit of geometric series. Anyone? For example, 1 plus 1/2, 1/4, 1/8. What's the limit for this one?
So is it the S formula or is it not that one?
Yes, the limit, not the sum. Sorry, not the partial sum, but the limit. So this is just 1 plus r square cube, that. So what's the limit in this case?
Is it infinite, sir?
Mm, nope. Why is infinite? And formula? So this geometric series, so the limit would be 1 over there. Okay. So then now the question is, so this is the basic thing. We use this almost all the time for this type of problem. Always start with the, another operation is, forget, substitutions. For example, this one. This one here. F of x equal 1 minus 1 over 3x. Final power series representing f of equals 1 over 1 3x. Okay. Okay. So this is like just like 1 over minus u with u equals 3x. Okay. And this one is, well, this is the limit of geometric series. Of ratio equals 3. Okay, so this is u to the n. Okay, so that means 3x, sorry. 3x. Or you can say something like, look like this one. 3 to the n, x to the n. Sorry, 1/3. Yeah. Okay, so that's this is this power series. Another thing. Well, what about this one? F of x equals x squared times 1 minus 3x. Okay, so let's build up from, so let's say this is d of f, because we use f here. Sorry, g of x. Okay, so this f of x. Now let's see. Oh, sorry, forgot to mention this one. From now on, if we mention something like this, a series, then we mentioned it for the, for what values of x this is true. So this is true for what? Right? Because this geometric series, oh, not even one. Geometric series convergent for ratio less than 1. Okay. All right, so that's 1. So this is x squared times 1 over 3x. It means f of x. F is this part. Okay, that's why it's just x squared times that sum there. Okay, so that means 3 to the n. x, you plug it in inside, so n plus 2. Okay, so this is the power series for this function g, and that is true only for this. Doesn't change the convergence set. Convergence set does not change during these operations. So you start with convergence set between -1 and 1. You multiply by x squared, still same convergence set. Okay. All right. What about this one here? Hmm. Okay. For example, uh, let's do the let's say, what about this tangent inverse of 2x? One. So in this thing here is that let's try to imagine what kind of process can you the process you should get tangent inverse from something that looks like 1/4. To get tan inverse from this is limit of geometric series using, you can use substitutions, arithmetics, and calculus operations. Oh, I should mention here what mean by calculus operations. Calculus operation is you of course limit, differentiations, and integrate term by term. Okay. So if, what you mean term by term? If you have this as a, say, so then f prime would be, would you take the derivative of each term separately. So you have a1 to a2 x. So this is 3, 3a3x squared. Okay. And you can do also, what about this one? From 0 to t, for example. Well, that's the same. So that's a1t plus 2a2, sorry, here, a1 t0 2 plus 3 cube over, oh, here. Okay, so term by term operation. Okay, so here, let's see how we got this tan inverse 2x. Okay, so let's think about this one here. So let's see. Start with this, and you can make this one. Of course, you can think this is as oh, let's see. Why? Because minus x, right? So we can start from here. So this is a sorry, geometric series with ratio minus x. Okay. So then you can do also 1 over 1 plus x squared. This is substitutions. You replace x by x squared. Okay. And then, well, from here you can get tan inverse x by doing integrations. Okay, so you already get the tan inverse arctangent. Okay, and then again you can use 2x another by another substitutions. Okay, so this is the process. All of this process, then, all right, so let's start with this. 1 over x, 1 plus x is okay. So this is, I'll write down the just the to the right longer, so not using the sum as sigma notations. Okay, so this is going to be 1 minus x squared, right? Minus x cubed plus x to the fourth, dot, dot, dot. Okay, and this is correct for x between -1 and 1. Okay, so doing substitutions, substituting x squared, so you replace x by x squared, so you get 1 minus x squared plus x to the fourth, x, what's what, 6. There. Okay, you can write this down as x to the, we call it 2n. Sorry. And this is also correct for not one. Yes. Okay. And now you integrate the t from 0 to x. Then you get tan inverse x. Okay. So integral 1 by 1. This gives you just x. This gives you just, how you call this one? X squared over square. Let's see. X to the 4 over okay. And you can write this down as sigma okay, from 0. You can integrate this one. Just remains. So you just integrate this one here. Okay. So you have 2n plus 1 right, at 1. And then x to the plus 1. So that gives you this series. And this is true for x between -1 and 1. Okay. So now when you think about tan inverse, let's see, arctangent of 2x. So you're replacing this x by 2x, so doing substitutions. Okay. When you do substitution, so this is what you get here. Just replace x by 2x. Okay. And this is 2n plus 1. 2n plus 1. Sorry, this is 2, 2x. Yeah. But let's see here. But this is true for 2x between -1 and 1. That means x between -1/2 to 1/2. Okay, so the convergence set is this one. And this is the, for this one, uh, power series for arctangent to x. Here, problem. Okay. Questions? Right. Um, see, just one more example from problem 9. Right. Problem 9 is this is problem D, for example. It's looking for uh, a series expansion for ln of 1 plus x over 1 minus x. uh, plus uh, using power series operations. Power series. Okay. Let's see here. F of x minus is just difference. Property. So we need to find the series for this, and series for this one. And how you get this one? How you get this one? All right. And let's see. You always start with a geometric series. Okay, so we call this the 1 over plus x. If you integrate this one, okay, so you get ln of okay, so this one. So this turned out to be integral from this one. And if you then you get okay, so you get expansion for ln of this one. Sorry, just finish this up by doing integrations. Okay, so here uh, so 1 over 1 plus x. Remember this one? This is the so let me write this down. 1 minus x plus x minus x squared plus x x squared cubed. And this is true for x as the absolute value. All right. And if you integrate this, okay, you get ln of plus there. And you get integration for this, just x plus x3. And you can one. That's for x. So like okay. And here it is just substitutions. Replace x by minus x. Okay. And oh sorry, this is plus minus plus Let's see. 2, 1, 2, 3, 4. 1, 2, 3. Oh, this is 4. 3. Power 4. Yeah, this is 4. Replacing x by minus x. Okay, this is just still the same because it's square. This gives you and then become minus. Right, so it's x. This is still same. This becomes minus. This is the same. This is become minus. Okay, and this is 4. All right, and then you subtract. Okay, what you get here. Just 2x, and you subtract becomes 2 also. This is cancel. Power 4, you get 2 of this. So 1. So I write down. This minus this 2 times this cancel. And you can find something else here. Level twice. Yeah, that remain. Okay, so this is the power station expansion. Okay, we'll stop here and we'll continue this tomorrow. Okay, questions? Short questions? All right, maybe not, and just share this material with you so for you to study for the joint quiz. All right. Stop the share, stop recording.